Hangzhou's chief hypergravity facility shatters limits with centrifuges spinning samples at 1,900 G. Zhejiang University's engineers accelerate material tests. Chief's experimental halls cover 34,560 square meters of floor space dedicated entirely to hypergravity exploration. Is almost equal to $287 million. Investment approved in 2018 by China's National Development and Reform Commission under the 13th Five-Year Plan. Geological processes, such as crack propagation, phase separation dynamics, and structural fatigue, normally unfold over centuries or millennia. Here, they play out in minutes. High-speed imaging systems synchronized with millisecond precision data loggers record every nuance of deformation, forging new pathways at the intersection of physics, geology, and engineering. In the seismic Geotechnics module, scaled dam prototypes and engineered slope assemblies undergo gravity intensification to simulate earthquake shocks. By subjecting molten precursor blends to intense G fields alongside synchronized thermal, acoustic, and chemical stimuli, teams produce microstructures with exceptional toughness, corrosion resistance, and heat tolerance. Initial experiments have yielded titanium matrix composites with 20% higher tensile strength and 30% finer grain sizes than gravity-quenched counterparts. By applying up to 1,900 G in controlled bursts. Endorsed in 2018 under the 13th Five-Year Plan and backed by a multi-billion yuan investment portfolio, it embodies a strategic vision that pairs scale with interdisciplinarity to tackle grand challenges. Resilient infrastructure in seismic zones. Phased commissioning is set to conclude by late 2026, cleaner energy from deep-sea reserves, and advanced manufacturing of high-performance materials, at which point researchers will enjoy seamless experiment scheduling and continuous data streams. As Chief spins up to full operation, the international community watches closely, anticipating breakthroughs that emerge when gravity itself becomes the laboratory tool of choice that push boundaries. Swappable in under 4 hours, they enable rapid iteration of multi-physics experiments that combine hypergravity with temperature cycles or fluid flow. Agricultural researchers probe how hypergravity affects root architecture and nutrient uptake, paving the way for crops suited to extraterrestrial farms. Pharmaceutical labs accelerate drug crystallization under centrifugally enhanced conditions, improving compound purity and solubility profiles. Over hundreds of cycles and biophysics studies into protein-folding pathways relevant to neurodegenerative disease research. Aerospace collaborations employ Chief to simulate atmospheric reentry stresses on thermal protection alloys, supplementing traditional wind tunnel tests with rapid, high-fidelity data. Additional proposals target next-generation battery electrodes, subjected to extreme rotational forces to model degradation. From next-generation battery testing and biomedical cell culture under simulated Martian gravity to exoplanetary geology simulations, Chief's research frontiers stretch across science and engineering, ready to unlock discoveries that reshape our understanding of the extreme. Engineers identify precise failure thresholds. Chief has firmly overtaken every prior centrifuge installation, including the U.S. Army Corps' 1,200 G-tons unit. As a centerpiece of the Belt and Road Science Alliance, Chief offers international research teams competitive access slots and joint funding opportunities, inviting collaborations from Europe, North America, and beyond. Whether testing seed germination under elevated gravity for future space agriculture or investigating phase-change materials for hypersonic applications, global scientists converge on Hangzhou to push the boundaries of experimentation and refine slope stabilization methods that will bolster critical infrastructure in quake-prone regions. Next door, geological modeling bays replicate pressures encountered tens of kilometers beneath the Earth's crust. Reinforced fixtures anchor giant rock cores while high-resolution acoustic sensors detect microfractures, enabling real-time study of fault slip behavior, rock creep, and mineral metamorphism, generating datasets rich enough to underpin predictive models for aerospace components and earthquake-resistant structures. These ice-like compounds trap enormous methane reserves under seafloor sediments and permafrost. Under hypergravity conditions, scientists cycle hydrate formation and dissociation with unprecedented control, Early trials indicate a 15% gain in controlled dissociation efficiency compared to conventional high-pressure vessels. Equipped with ultra-high-pressure fluid injectors and precise temperature regulators, this chamber enables safer and more efficient exploration of cleaner energy sources while minimizing seabed disturbance. Modular test baskets allow samples to be exchanged in under 2 hours, maximizing experimental throughput. By transforming months, or even years, of stress testing into single-day experiments, Chief accelerates innovation and slashes resource requirements, marking it as a true game-changer in hypergravity science. After groundbreaking in mid-2020, Zhejiang University led a collaboration of architects and mechanical engineers to install advanced magnetic bearing systems that virtually eliminate friction and sophisticated vibration-damping modules that stabilize the rotor assembly. Each centrifuge operates within a vacuum-sealed enclosure to minimize air resistance, ensuring data integrity at extreme speeds. An integrated network of real-time sensors continuously monitors load distribution, temperature gradients, and stress concentrations, enabling researchers to capture high-fidelity measurements of material responses under radial accelerations that mimic conditions deep within planets or beneath ocean floors. Dominating this space are 3 colossal centrifuges, each outfitted with 2 precision-engineered arms exceeding 20 meters in length and carrying custom test baskets at their tips. The first unit transitioned from installation to full calibration this spring, while the remaining 2 are on track for commissioning by December. At maximum spin, these rotors achieve tip velocities above 50 meters per second, generating forces up to 1,900 g-tons, the product of gravitational acceleration and sample mass. In comparison, the U.S. Army Corps of Engineers' premier centrifuge peaks at 1,200 g-tons, making Chief the new global leader in raw hypergravity capacity. Simulate deep Earth pressures and recreate abyssal sea conditions in moments. Backed by 2 billion yuan and a national mandate, Chief drives seismic safety research, clean energy hydrate studies, and advanced alloy design, condensing months of experiments into seconds. On a sprawling 5.9-hectare campus in Hangzhou, behind this engineering triumph lies a 2 billion yuan. Perhaps Chief's most breathtaking feature is its ability to compress timescales. Chief's 6 purpose-built experiment chambers span disciplines. A dedicated deep-sea engineering chamber tackles another frontier: natural gas hydrates. In the advanced materials chamber, researchers exploit hypergravity-driven phase separation to forge novel alloys. Complementing these chambers are 18 mobile experiment units, self-contained platforms equipped with sensors for magnetic fields. With sustained hypergravity runs at up to 1,900 g-tons, Zhejiang University has already formalized partnerships with leading institutions and industry consortia. Nationally, Chief exemplifies China's shift toward big science infrastructure. Thank you for watching. We hope this journey into Chief's extreme gravity frontier has ignited your imagination. Be sure to subscribe and click the bell for upcoming exciting deep dives into cutting-edge science and engineering innovations that push boundaries. Until next time, stay curious, keep exploring,